In this video, we're going to look at area under some polar curves. So we're going to be focusing on limacons, in this case with the inner loop. So sometimes we are being asked to find the area of the inner loop. Sometimes we are being asked to find the area of the outer loop. Sometimes we have to find the area of outer loop area, or sometimes we are asked to find the area in between the loops. Okay, so let's see, find the area of the inner loop of 2 plus 4 cos theta. So how does this graph look like? 2 plus 4 cosine theta. So it's going to be on the positive x-axis. It's going to go all the way up to 6. It's going to go up to 2 here, negative 2. That's going to be something like this. That's how my graph is going to look like. It's going to be symmetric on both sides here. So let me make it. All right, that's how the graph is going to look like. So now I do have an inner loop and outer loop, and I'm only looking for area of the inner loop here. For that, I need to figure out where does the inner loop start and where does the inner loop end. Inner loop starts and ends when I'm back at the pole. So inner loop starts and ends when I am back at the pole, which means when r is 0. So I'm going to plug r is equal to 0 and solve here. That would be 0 equals 2 plus 4 cosine theta, which is negative 2 is equal to 4 cos theta. Negative 1/2 is equal to cos theta if we divide both sides with 4. Now, where is cosine negative half? Let's think about it. Cosine is half at pi over 3, but we are talking about negative, and in all students take calculus, cosine is negative in the second and the third quadrant. So my coordinates, or the points where cosine will be negative half, that would be in the second quadrant and in the third quadrant. And the reference angle is pi over 3. So in the second quadrant, it would be 2 pi over 3. In the third quadrant, it would be 4 pi over 3. So these are the points where the inner loop starts and inner loop ends. Okay, so now I'm going to go ahead and find the area, integrate. I know the bounds of integration now. 4 pi over 3 and 1/2 r squared, which is 2 plus 4 cosine theta squared d theta. Let's go ahead and plug this into a calculator. Go ahead and use an integral calculator. Turns out to be 2.174. 2.174. Okay, so that's the area inside the inner loop. So we found the area just for this region. And when we're going to find the area of the outer loop, we will see that the inner loop area is covered in here. So sometimes we're going to be asked to find the area in between the loops. And sometimes we're going to be asked to find the area of the outer loop. So the outer loop area will include the inner loop area. It will be covering it again. It would be overlapping. But if you're looking for the area in between the loops, then we would have to subtract the two areas. Let's see the second example. Find the area of inner loop of r is equal to 1 minus 2 sine theta. Same kind of story. Let's go ahead and graph it. 1 minus 2 sine theta, it's going to be majority will be on the negative y-axis, and that's how the graph is going to look like, and we're finding this area. It's going to be 3 here, 1 at this point, and negative 1 here. Okay, so where does inner loop start and end? That's the big question, because that's what's going to give me the bounds of integration. Where does the inner loop start and end? Where does the inner loop start and end? So the inner loop starts and ends at whenever r is equal to 0, whenever I'm back on the pole. So 1 minus 2 sine theta is equal to 0. 1 minus 2 sine theta is going to give me whenever this is equal to 0. So sine theta is equal to half. When is positive sine theta equal to half? Positive sine theta is equal to half whenever theta is equal to pi over 6. And in the second quadrant, whenever I'm at 5 pi over 6, because sine is positive in the first and second quadrant. So the area of inner loop is going to be, you can call it AI if you want. Sometimes I represent AI as area of inner loop, AO as area of outer loop, and AB as area in between the loops, if we are being asked to find it. So start with pi over 6, go to 5 pi over 6, 1/2 r squared d theta. Again, I'm going to use the calculator. So integral calculator, the bounds are 1 sine. The bounds are fractions, pi over 6, 2 fraction 5 pi over 6. So that turns out to be 0.5435. 0.5435. All right, let's see next example. Find the area inside the larger loop and outside the smaller loop. So this is the question where I need to think about where does the inner loop starts and ends, and how does the outer loop get traced? Might be helpful to go ahead and just pick several values of theta and make a table and graph this curve and see where do you start and where do you end. So what I'm going to do here is let's find where does the inner loop start and end. I do need that information also. Where does the inner loop start and end? The inner loop starts and ends whenever 1/2 plus cosine theta is equal to 0. 1/2 plus cos theta is equal to 0. That means whenever cosine theta is negative 1/2. So when is cosine theta negative 1/2? We just talked about that it happens in the second quadrant and it happens in the second and third quadrant. So that is going to give me the reference angle is pi over 3. So this happens at 2 pi over 3 and 4 pi over 3. So I can go ahead and find the area of inner loop, and that's going to be starting at 2 pi over 3, going to 4 pi over 3, 1/2 r squared, 1/2 plus cosine theta squared d theta. Let's find the area of the inner loop using the calculator, and I'm going to leave the integral entered because later on I'm going to have to use it again. So I'm not going to delete. I'm going to go back and leave my integral entered here. So I would have 1/2 So area of inner loop turns out to be 0.1358. 0.1358. 0.1358. Okay, now big question is we need to find out how does the inner loop get traced? Or where does inner loop start and end? Outer loop, sorry. Where does outer loop start and end? Where does outer loop start and end? Start and end. Okay, so we can see when r is equal to 0 or when theta is 0, we know that's where we start. When theta is 0, that means r is equal to 1/2. So this is where I begin and I start tracing and I go all the way up to here, and at this point I will be at 2 pi over 3 because that's when the inner loop begins. So starting here all the way up to 3, the little bit problem or question is I'm not sweeping my complete circle. I'm not closing the curve. I have this part open. So we cannot start at half. Oh, sorry, it was at the top. It was right here. That's where I start. So starting over here, going this way, that's what I'm doing, and then I'm at 2 pi over 3. That's when the inner loop starts. But we can see that if I start at half, if I start at theta equals 0, I'm not able to complete my curve. This pink region is left uncovered. So I have to back up a little. I cannot start at theta is equal to 0. I have to start a little bit behind. Where do I start? How far behind do I start? For that, it's actually very helpful to see the graph of r equals 1/2 plus cos theta. So this is a graph of cosine theta shifted half units up. We can use trigonometry to graph it, or I'm going to just use quickly Desmos so that I don't spend too much time on graphing here. Although it's very simple, all these graphing curves will be very simple if you remember graphing the trig functions. So r equals half plus cos theta, going to Desmos. So that's how r equals half plus cos theta looks like. If you look carefully here, this is where your outer loop and your inner loop. So outer loop begins at negative 2 pi over 3 and then ends at 2 pi over 3. Inner loop begins at 2 pi over 3 and ends at 4 pi over 3. So the bigger one will be always your outer loop, smaller one will be the inner loop. So negative 2 pi over 3 and 2 pi over 3 and 4 pi over 3. So I am starting at negative 2 pi over 3. So negative 2 pi over 3, positive 2 pi over 3, and 4 pi over 3. And that's how my curve is swept. And we will go on and it will continue repeating the process. We can go on. So there's two things that have to happen. Either when I'm at 4 pi over 3, I'll have to go a little further, or I have to start a little earlier to be able to close the loop. Instead of starting at theta is equal to 0, instead of starting over here, I need to come back a little so that my loop is closed. And I would be starting at negative 2 pi over 3. So for the outer loop, area of outer loop, it would be negative 2 pi over 3. And the outer loop ends at 2 pi over 3. The inner loop starts to being made at the point 2 pi over 3, and then we have 1/2 r squared d theta. Let's see now, using the calculator, negative 2 pi over 3 to 1/2 plus cos theta. I'm just going to be using x. And remember, when you square it, make sure you use 2 parentheses when you're squaring the r, so that you're not just squaring your x. Otherwise, you will end up making a mistake. And this area turns out to be, let's see, 1/2 times 1/2 plus cos x squared. And the bounds are fractions, negative 2 pi over 3, pi over 3 to 2 pi over 3. Okay, so this area turns out to be 2.22. 2.22. Now keep in mind, when we're going to be sweeping this area, the inside loop is also getting covered in here. And we were actually looking for the area in between. We were looking for the area in between. So what we were looking for is, let me go ahead and redraw it. When we sweep the outer loop, the inner loop area is also covered in here. Okay, so we were looking for this area only. So what we have to do is we will have to subtract the area of outer loop minus the area of the inner loop, and that's going to give us the difference, which is the area in between the loops. So area between the loops, I always represent it. So this was area of outer loop. Area between the loops would be area of outer loops minus area of inner loops. And that turns out to be area of outer loop minus area of inner loop. Outer loop area, we just found it's 2.22. And the inner loop area, we did find that was 0.1358. 0.1358. 0.1358. So 2.22 minus 0.1358 is 2.08, 2.084. So that's the area in